Hi, thank you so much for coming to this talk. This has been one of the best conferences I've been to in a long time. I've really been enjoying my time here. But today I'm going to talk about supersingular elliptic curves. And, oops. So a little bit about me. I'm a current PhD student who flew all the way from the University of Vermont. And I'm working on isogeny-based cryptography, which is a form of quantum-safe cryptography. So I work in mathematical cryptography, which is cryptography that uses mathematical constructions that are computationally hard enough to be resistant to attacks from quantum computers. So I'm kind of foreseeing the future in a way because we don't have large-scale fault-tolerant quantum computers yet. And I'm also originally from Trinidad and Tobago, which is the island that's just above South America. Okay, so the challenge today is that quantum computing provides a significant threat to our classical methods of encryption. And in 2017, NIST, which is the standards committee, made a call for digital signature schemes for post-quantum standardization. So companies such as Google, Microsoft, IBM, et cetera, are already investing billions of dollars into quantum computing. So for example, this right here, I believe it's Sycamore at that point in time, but it's Google's quantum computer, which claims to be able to perform a task that a supercomputer takes 100,000 years to perform in just 200 seconds. So what does it mean if quantum computers can perform tasks faster? Well, since decryption is based on specific hardness assumptions or the hardness of solving certain problems, it means that quantum computers could break our current classical methods of encryption by solving these problems faster. And the implications are threats to our national and personal security. So modern cryptography today relies on trapdoor mathematical problems. And what I mean is that, say, if we're given an x, you run some kind of function, f of x, that is easy to compute, but its inverse, which is f inverse of x, requires some secret information to calculate. So without this information, it is difficult to compute f inverse of x. And so quantum-safe cryptography takes these similar ideas and these types of problems, except that we're assuming that the computational hardness properties are considered when in a world where quantum computers exist. And this is because the way encryption classically works is that it relies on problems that are easy to solve, but difficult to reverse engineer. So if we think about the classical encryption case of Alice and Bob, who both know a key to unlock a message, but Eve, who is not minding her own business and is instead listening in, trying to reverse engineer the message that they're sending to each other, we want to make sure that this is not possible. So this is because, the way we're able to do this using trapdoor mathematical problems is that we use techniques such as integer factorisation to make the complexity of computation impractically long for a classical computer to factorize into its component prime numbers. So another problem, or similar problem, is called the discrete log problem, or DLP. So a quantum computer can solve these problems substantially faster, rendering classical encryption systems insecure. So on the left, this is from 2015, Quantum Magazine made these quantum breakable and quantum security kind of charts, a list of different schemes that are quantum safe versus quantum breakable. And you can see up to today that multivariate cryptography since then is no longer considered safe from quantum attacks. So then it asks the question, what problems are quantum safe? So some examples of existing mathematical problems that are considered quantum safe are the shortest vector problem in lattice-based cryptography, learning parity with noise for learning with errors, and pathfinding in isogeny graphs, which is what I work within. So the truth is that in a world with quantum computers in the future, we need more similar constructs based on hard mathematical problems to be resistant to quantum attacks. So isogenies, actually I wanted to point out this paper, which came out last year by Eli Chen, shocked the entire quantum and cryptography community because it claimed to provide an algorithm that could break lattice-based cryptography, and lattice-based cryptography, until most recently, is considered one of the more reliable constructions for quantum-resistant cryptography. So if there's a flaw in lattice-based cryptography and some algorithm can break it with a quantum computer, we're in a lot of problems. Okay. So isogenies, which are derived from a specific type of construction called supersingular elliptic curves, are a promising new type of encryption that starts from an elliptic curve pairing of a type supersingular to generate a large random graph from Ramanujan properties. So these properties make a walk along a path appear random to an onlooker and make this particular type of encryption, which is called isogeny-based encryption, quantum safe. So this is what an ordinary graph on the left-hand side looks like, which would be generated from a general elliptic curve versus an isogeny graph, which is to the right-hand side. So the distinction is that the ordinary graph is generated from ordinary elliptic curves, and the latter is generated from what we work with, which is supersingular elliptic curves. So you can see how random it is and more difficult to traverse. And that gives it its hardness properties that are resistant to quantum computation attacks. So two current problems that I work within in isogeny-based cryptography are broadly the issue of scalability and the need for reduced computation within isogeny-based protocols and provable security, specifically something called the known endomorphism ring problem in isogeny-based cryptography. So how might we construct cryptography using isogenies then? So let's look at one construction, which is called the CGL hash function. So to do this, I'm going to start with a hash function, a classical one. So for example, if we take the string as an input, I love CBAS, we can use an algorithm, for example, SHA-256, to create the string, which if I didn't know what SHA-256 was, I couldn't reverse engineer this message. So this is a Charles-Gordon-Lauter hash function, and we're going to do a similar construction, but as our output, we want to have a random string of ones and zeros. So the first thing that we do is start with something called a known endomorphism ring. And it's usually called an unknown endomorphism ring because we don't want anybody to know this value, or if they do know this value, they should be a trusted person. So for example, in this CGL, or Charles-Gordon-Lauter hash function, you start with a starting vertex, that V value. And so this value is called E sub 0, and you can't go backwards in this graph. So this is a walk along a graph. So you either take a left or a right, where 1 is left and 0 is right. And so our next step is 1, and then 1, 0, 1, and then 1, and then 0, and then 0, and then 1. But someone still needs to start that walk, and this person knows the starting endomorphism ring. And so our secret at the end, our output, is 011,001, which is equivalent to, say, the string that we got in our original hash function. So the state of the art in this area gives a method to compute a statistically zero-knowledge proof of isogeny knowledge that is compatible with any base field. So by proof of knowledge, what I mean is that every party to the computation must verify each other party's computation. So this can't be avoided. So the cost of the computation of the final secure supersingular elliptic curve increases linearly with the number of parties who wish to participate in constructing this curve. So what we did instead is, so this is a typical proof, which is called a proof of isogeny knowledge. We use something called a proof of isogeny computation instead. So contrary to previous work, the prover only needs to compute the isogeny walk that needs to be verified. So typically, in computing a chain of n isogenies, each preceding node must verify the correctness of the proof of each preceding node, which is computationally linear in n. So this would be a second node, and so on. So this is called the proof of isogeny knowledge. And as some isogeny protocols constructions scale, it can be computationally expensive. So our goal was to reduce this by using something called a folding scheme, which was taken from blockchain because it was COVID times and I was interested in blockchain. So I learned about folding schemes. And as it turns out, when we used the folding scheme, we were able to combine the proof of computation such that we could verify in a single proof asymptotically, the same time as it takes to verify each of the proofs individually. So to do this, we used something that existed on the market called NOVA, which is a SNARK, a type of zero-knowledge proof. And so we empirically built this system to prove the execution of the circuits, computing the isogeny, rather than producing the original proof of knowledge. So this proof could then be used as part of the verifiable folding scheme, NOVA, which reduced the complexity of an isogeny from O of n to O of 1 by providing at each step a single proof that verified the entire preceding chain. So then we evaluated our methods to show that the circuit grows linearly with the length of the isogeny walk being computed at each folding step, with the verification of the entire walk taking just a few seconds. And so this is work that we presented last year at QCE, which is a quantum computing conference. So moving on to our second problem, and this is something I'm working on. Remember I spoke about that original E sub 0, which is assumed to be a trusted party? Well, this is some work that I presented at QIP, which is a quantum information processing conference this year, that we're working on still, which shows some constructions for securing that original E sub 0 value. So we're using a mix of encryption techniques like fully homomorphic encryption and secure multi-party computation to enable us to secure this E sub 0 starting point so that no one person will know the starting point. Because if they know the starting point, essentially the entire walk will be revealed, or it could be public. So instead, what we do is we start by generating a key among n parties. So we return the public key so that each person in the party, so n parties, receives a fraction of the share. So no single person could decrypt the entire, knows the E sub 0 value. So then the parties generate random strings for the random walk circuit and encrypt them. The parties send the encrypted randomness to the original E sub 0 to a server, which is also considered to be trusted. The server runs the circuit in fully homomorphic encryption and computes the entire walk using the encrypted randomness. And after this computation, the parties decrypt the entire walk using the shared secret key. So this means that no single party can decrypt the walk, and no one knows the original E sub 0 individually. And so another assumption that we have to make, if anybody has been in, say, Signal or WhatsApp or any such group, is that you expect that, or even Discord, for example, your users are not always online, and you can't expect that they're also honest. So this is another version of the protocol that we're working on, which is a hybrid version where we consider that some fraction of the party is semi-honest, so some may be malicious, and that they're not all considered to be online. And in this case, according to most of these cryptographic protocols, you usually consider that no more than a third of the parties are malicious, and that you have at least 2 parties at any given time online. So in summary, we're currently working on these 2 ideas of trusted computational methods for the distributed setting of isogeny-based cryptography, and this is an extension of our past work, which used the folding schemes that I spoke about that we presented at QCE 2024. So finally, this work is kind of a culmination of work that was started in the number theory community. Typically, if you said isogeny-based cryptography, I know that's a mouthful, it was among number theorists, and a lot of the work was theoretical. And now that we're starting to build these schemes, bearing in mind that there are quantum computers that exist in the world that will be scalable and fault-tolerant one day, we want to make sure that these are deployable in practice. And so for that, I had to have a mix during my PhD of a computer science advisor and a mathematical number theorist advisor. And so I'd like to say thank you to Joan Eyre, who's my CS advisor, and Krystal Maughan, who's my math advisor. Thank you.